This topic involves using a straight line to approximate a function at certain locations. It's called linear approximation, and I'll start with an example. Compute the equation of the tangent line to f of x equals sine of x at x equal to 0. So if we want to compute the equation of the tangent line, first thing we have to do is take the derivative and then plug in x equal to 0. So we'll start f prime of x equals cosine of x. F prime of 0 equals cosine of 0, which equals 1. So this tells us that the slope equals 1. Next, we need a point. Well, since sine of 0, f of 0 equals sine of 0, which equals 0, we can use 0, 0 as a point. And then you'll remember from the slope-intercept formula, or maybe it's the point-slope, I think it's point-slope form, we can get the equation of the tangent line by doing this. And here, in this case, y0 and x0 are both 0, so we'd get y minus 0 equals 1 times x minus 0, or more simply, y equals x. So the tangent line is simple as you can possibly get, y equals x. What I've done then is graphed sine of x and y equal x on the same graph. So the straight line, of course, is y equals x, and the curved one is y equals sine of x. And what I'm interested in here is not how much they're different. I calculated this tangent line at 0. And remember when we talked about concavity and things like that, notice how when it's concave down, it bends underneath of the tangent line, and when it's concave up, it bends above the tangent line. But I'm more interested in right in the middle here. Notice how close the two of these functions seem to each other in this small region. Let me circle it. Somewhere in here, they virtually seem like the same graph. And in fact, let me zoom in some on these two things, and look what we have here. I would say that, to me, they look anywhere from here to here. They look the same to me. So I would say in this region, from negative 0.2 to 0.2, sine of x is the same as y equals x. So let's put less than or equal to. Sine of x is approximately x. So with this in mind, let's pick some numbers that are small in this region and see how close of an approximation it is. For example, suppose I want to do sine of, I didn't mean to do that, sine of 0.1. Well, that's approximately 0.1. Let's test it out on your calculator. Now, as a reminder, when using your calculator, make sure that the mode you are in is radian. That way this will all work. Whenever you're dealing with trig functions, and here when you're treating an angle or a distance interchangeably, you want to be in radians because degrees cannot do that. So let me get out of that spot. I'll second quit. And let's see how close this is. Let me do sine of 0, well, sine of 0.1. Let's see how close this is. Look at the sign of it. So we have 0.0998. If you rounded to 1, 2, or even 3 places, even 4 places, they would be about, you'd have the same answer. And in fact, what is the error that we have here? If I wanted to calculate the error, well, let me come back here for a second. The calculator, the calc, you just grab that portion of it. Or I'm sorry, 0.1 minus this number. Let's just do that. So I'll do 0.1. Let's clear that. If I do 0.1 minus the answer, it'll give me how much different this is. This is, remember, E negative 4 means there's 3 zeros in front of that. So this is approximately 0.0001 66. So I'm going to put a 7 here. Well, let's try something in the negative. Let's try sine of negative 0.2 is supposed to approximately be negative 0.2. Let me see what the calculator has to say about it. And let's take a look and see what the error is then. I'll do negative 0.2 minus negative 0.198669, and that is approximately, I'll do the same thing as I did before, negative 0.2 minus sine of negative 0.2 unbelievable 0.00133 0.00133. So you can see even at negative 0.2, this is not too far off. We could use these numbers instead of actually having to try to calculate the sign and be fairly accurate. But now watch as we start to get away from there. Let's move away to where it's pretty obvious they're different. And let's take a look at 0.4. So sine of 0.4 is approximately, now let's use the calculator to do this. So sine 0.4, enter, 0.389. And now you can see that the error would be 0.4 minus 0.389, which is approximately 0.011. You can see the error is getting more vigorous now, although it's not horrible. But clearly you can't, it's getting less accurate, and clearly the farther you move away, the more these two curves are going to bend away from each other, and the accuracy will no longer be valid. And especially you can see if you go way, way, way far away. Now the good news, though, is that if I want another linear approximation somewhere else, I calculate myself a tangent line at that particular point, and then I can use that tangent line to approximate the actual y values. I'll show you what I mean. In general, we'll have some sort of a curve, let's say. Maybe that's our f of x. And you find yourself a tangent line at that curve, to that curve at some point. And for a small area around, for a small region around there, the accuracy looks like it would be pretty good, especially if the curve is not just a sharp bend. If it has a sharp bend in it, this isn't going to be very good. But if it's more smooth, you can see that these are going to hug each other for a little bit around there. Well, the equation in this line is y equals mx plus b. But how do you get all these numbers? Well, the m, let me put the point here. I'm going to call the point x sub 0. Better than that, I'm going to use the letters that most books go with. I'm going to call this a, and then over to the left on the graph, that y value is f of a. All right. So to get this equation, you typically, the y equals mx plus b, you do y minus y0 equals m times x minus x0. Okay, so let x0 be the a that I'm talking about. Then y0 will be f of a. Y is going to go by f of x. M is the derivative at a. Then, if you add f of a to both sides, you get this. This here is called a local linear approximation. In fact, most books actually give this thing a name itself. And realistically, when f is not exactly at a, when x strays anywhere away from a, this here is the equation of this line. Okay. This here is still an equation of that line. There's the m, x minus a, plus, if you will, want to think about it as b, but it's probably not going to be b. But even so, it takes the same format as a slope intercept format. So anyways, actually what we should probably put is this, an approximation. And then we usually define this thing, L of x equals f prime of a times x minus a plus f of a is called the local linear approximation to f of x at x equal to a. So the local linear approximation is the thing to keep in mind. Let's go ahead and put box around that. Many times we'll just be asked to find the local linear approximation. Sometimes we'll be asked to find some other things. Let me do an example. Compute L of x for f of x equals the square root of x at x equal to, let's do 2. So I would calculate L of x equals f prime of 2 times x minus 2 plus f of 2. And let's see what happens. F prime of x equals 1 over 2 radical x. So f prime of 2 equals 1 over 2 radical 2. So the formula for L of x then is L of x equals f prime of 2 is the 1 over 2 radical 2 times x minus 2 plus f of 2 is the square root of 2. So there's the local linear approximation at x equal to 2. Use L of x to approximate the square root of 65. If I want to approximate this, what I want to get is the square root of 65 is approximately equal to something. And I don't want to go to the calculator just yet. Let's first calculate the L of x. That is f prime of a times x minus a plus f of a. And what is my f going to be? Well, I think a good idea is to allow f of x to equal the square root of 65. Not the square root of 65, the square root of x. So then, what this will end up looking like is 1 over 2 times the square root of a times x minus a plus the square root of a. And that will be used for my approximation. Now, if I want to do this easily by hand, I should probably try to choose an a that is close to 65, because the approximation will be good if I'm close to it, but one that has a good square root. Luckily, 64 is really close to it and has a square root that is easily done. So I'm going to let a equals 64, so that Lx equals 1 over 2 times the square root of 64 times x minus 64 plus the square root of 64. This equals 1 over, square root of 64 is 8, so I got 1 over 16 times x minus 64 plus 8. And I can even go a little farther here. If I go 1/16 x, 1/16 times 64 is 4, so I have minus 4 plus 8. My L of x equals 1/16 x plus 4. This is a lot easier to use to get, it's a lot easier to calculate this than to actually try to do the square root of 65 by hand. So what I'm saying is this: f of 65 is now going to approximately be 1 over 16 times 65 plus 4. In fact, let me write that as a single fraction. 65 over 16 plus 64 over 16, that equals 129. This here is my approximation to the square root of 65. So the square root of 65 is approximately 129 over 16. Let me go back to the calculator and take a look and see how close that actually is. So I'll go second square root 65, 8.06222 6, and then 129 divided by 16, 8.0625. So we have, the way I could calculate my errors is to do this all in one line. the square root of 65 minus 129 divided by 16. And the error is negative 0.0002. So the approximation is very good. If I wanted to, I could probably get somewhere around the square root of 66, for example, square root of 66. That's still not far away from 64. So that's approximately 1 over 16 times 66 plus 4. Now in this case, it'll be 66 plus 64 will be 130 over 16. And if we do the calculations there, if I test the accuracy of the square root of 66 minus 130 over 16, and you can see the error is negative 0.00096. So it's still not that bad. And you can do these by hand. Let's try another one. Use L of x to approximate let's do the cubed root of 85. Is that a good one? Nope, that's not a good one actually. Do the fourth root of 85. Okay, so when I do my approximation, we're going to use f of x equals the fourth root of x, which you might find easier written as x to the 1/4 power. So then L of x equals f prime of a times x minus a plus f of a. And so the derivative of x to the 1/4 is 1/4 x to the negative 3/4 times x minus a. Careful there, that is an a. Plus a to the 1/4 power, or the fourth root of a. Now, what you might consider doing here is picking an a that will have a good fourth power, but one that's not too far away from 85. Can you think of one, a good fourth power that's close to 85, but whose fourth root you know? And you can try, I would try to let a equal 81, because the fourth root of 81 is 3. So then my L of x equals 1/4 81 to the negative 3/4 times x minus 81 plus 81 to the 1/4. I chose it because it's close and it has a convenient fourth root. This is 1/4. This, I'll tell you, students, you got to be careful with this. If I take 81 to the 1/4 power, that's 3. But if I take 3 to the negative 3, that's 1 over 27. And 81 to the 1/4 is plus 3. So we get 1 over 108 times x minus 81 plus 3. So this is my L of x. Now if I wanted to the fourth root of 85, so the fourth root of 85 is approximately, now I get to plug my x equals 85 in here. 1 over 108 times 85 minus 81 plus 3. That equals, this will be 4 over 108 plus 3. I'll simplify this a little because I know 4 goes into both of these, so this is, well, this is convenient. This is 3 and 1 over 27. That's a nice a nice number. Or if you wanted to, you can write it as 82 over 27. Either one of these will be sufficient. I usually ask for a real, an exact answer so that I know the students are showing me the steps and everything. So let's compare. So let's compare the fourth root. So I'm going to take 85 to the 1/4. And I'm going to subtract from it 82 over 27. And here the error is negative 0.0007. So once again, pretty accurate answer. So the whole game plan is to get this tangent line, if you will, here, and that's used as our approximation, so long as you pick numbers that are close. Let's try one more. The first one I tried with sine, that may throw you for a loop if that's the only example you see here. Use L of x to approximate cosine of 65 degrees. Now this might be highly bothersome because I said stick to radians, stick to radians, stick to radians. And I'm going to stick to radians. Let me show you. First thing I'm going to do is change this to radians. Cosine of 65 degrees is cosine of 60 degrees plus 5 degrees. That's cosine. 60 degrees is pi over 3. So this is pi over 36. All right, so what I'm going to do, this hopefully you can see that this part right here is a good candidate for A, and this whole thing is x, if you will. This whole thing will end up being what we use for x. But then this is the amount that's different, that it's off from A, if you want to think of it that way. So L of x equals f prime of A times x minus A plus f of A. F prime, well, what is f of x? What do you think f of x should be? Cosine of x. So let's say f of x equals cosine of x. So f prime of A will be negative sine of A times x minus A plus, all right, and I suggested the A be pi over 3, so we have negative sine of pi over 3 times x minus pi over 3 plus cosine of pi over 3. So all these numbers are numbers that we should know. This equals negative sine, this is negative radical 3 over 2 times x minus pi over 3 plus 1/2. Now it's going to be complicated to do this. I'm not going to be able to do this by hand, but my approximation, I'm going to throw in 65, which is really pi over 3 plus pi over 36. Watch what happens. Cosine of 65 degrees equals cosine of pi over 3 plus pi over 36. And I suggested this, of course, was the A. So this whole thing here is the x. This is approximately negative radical 3 over 2. So if I throw this in for x, I get pi over 3 plus pi over 36 minus pi over 3 plus 1/2. Those, of course, cancel. And we're left with negative radical 3. We do negative radical 3 over 72 pi plus 1/2. Let's see how close this is to the actual answer. Cosine of 65 degrees is approximately, this is using the calculator, let's try this one out. And I'm going to, just for the briefest of moments, I'm going to change my mode to degree. And then go back to the home screen and calculate cosine of 65. 0.4226, and then I'm going to do this stuff over here and see how close I was. So we'll have negative second square root of 3 times pi. I don't think I have to write the times, but I'll do pi divided by 72 plus 1/2. And the number we get is 0.424. So it's off in the third decimal place. And 5 degrees was a nice little step away. So 0.422, I'll say 0.4226. And this number up here was approximately 0.4244. So in all these cases, you're using a tangent line to approximate certain values.